Okay, thank you very much, Guillermo, for the invitation and the very kind introduction. So I will talk about weighted automata and quantitative logic. And first, let me give an outline. So I will start presenting the theorem of Büchi-Elgot relating automata and logic. And then I will look at the extension of automata to weighted automata and their behavior by Schützenberger. And then I will come to weighted logic and then to quantitative automata and logic. So to fix it, let A be an alphabet, a finite non-empty set, then A star is the collection of all words over A, and any subset L of A star is called a language over A. Now, given an alphabet, an automaton for us will be a quadruple having a finite set Q of states, then transitions, which are triples between states and, having two states and a letter. And we have, as usual, and we have initial and final states. And the path is a sequence of transitions, which fit together, Q0, A1, Q1, and so on, leading to Qn. And it's called successful if it starts in an initial state, so Q0 is in I, and it ends in a final state, Qn is in F. And then the language accepted by A is, L of A is the set of all words for which there is a successful path for the word in this automaton. So an easy example, let A be have just two letters, and suppose here we have an initial state and we have a final state. With A, we can go from the initial state to the final state. So in order to accept a word, it must start with A. And here actually we can loop the B's, and then the accepted language is the set of all A, B to the N is greater than or equal to 0. Now, in general, a language is called recognizable if there is an automaton such that L equals L of A, which accepts L. And in any course on automata theory, one learns a description of all recognizable languages, for instance, by rational expressions, by grammars, or by syntactic monoids, and so on. And what's not taught in the beginner's courses so often is a characterization by logics, and this is what I want to come to now. So in our example for this language, consider the following sentence. Phi, there is an x, and the variables here refer to positions in a word. Yeah, so there is a position in a word such that Ra of x holds, and this means at this position x, we have an A. So far this means the word contains an A. And for all y, for all other positions, they are greater than or equal to x. So this means x is the first position, actually. And, well, if y is different, so if y is a larger position than the first one, then y is labeled by b. Then we have a b. And so W satisfies this sentence intuitively if and only if W is precisely of this form, a b to the n for some n. Okay. Now I want to make this more exact. So we want to talk about words. So these are sequences of symbols. But in logic, we need a relational structure for talking about it. So we have to represent the word by a relational structure. And as underlying set, we take the set of positions, 1, 2, 3, up to n, and the usual smaller than relation from the natural numbers, and then unary predicates for every letter, and Ra comprises all positions between 1 and n where we have letter A, so where AI equals A. Now, clearly, well, if W1 equals W2, then the two relations, the relational structures are the same, but, well, more importantly, when they are the same, also the words are the same. So really, they represent precisely the words. And this is easy to see because if they are the same, the underlying sets are the same. So the two words have the same length. Well, the ordering is the same, that's clear, but also for all letters A, RA is the same. So this means RA are those positions where we have an A. So this means in W1, we have an A. I belongs to RA for W1, if and only if it belongs to RA for W2. So we have an A at position I in W1 if and only if A is also in position I at W2. And we have this for every A, for every letter, then the two words must be equal. In our example, so we can define L of phi as the set of all words where the relational structure satisfies the sentence. In our example, this was the set of all A, B to the N. Okay, so the syntax which we have here is we have a binary relation and we have unary predicates, and then we can form the usual formulas of first order predicate calculus, atomic formulas x smaller than or equal to y, RA of x, and then disjunction, negation, and existential quantification. And here we also need first layer of second order logic, namely monadic second order logic, meaning that we quantify only over subsets of the universe. That's the monadic. So, and we need to have a new atomic formula that an element belongs to a set, and the quantifier, there is a subset such that phi holds. And the interpretation of this is, well, is a subset of the universe. Okay, and then we have the following very important theorem by Büchi and Elgot. Let L be a language, then the following are equivalent. L is recognizable, and 2L equals L of phi is L is the language given by some sentence phi of MSO, monadic second order logic. And further equivalent notions are, well, as I said, that L is rational, regular, and so on. Okay, so notice that here we have a qualitative statement, both here and here, because here this means, well, there is an automaton and which accepts L, and the word is either accepted by this automaton or it's not. And here L is the language of all words satisfying the sentence, and again, here a word either satisfies the sentence or it does not. And now I want to come to a quantitative question. Well, how often is the word accepted by the automaton, or how much does it cost to accept it, to execute it? And here I want to talk about, well, how often is this true? How often does W satisfy phi? Which might sound strange for the logic point of view, but we will give this a precise meaning. So first, let's come to the first topic, which leads to weighted automaton. So they were introduced by Schützenberger already in the 1960s. And here's an example. It's an artificial example. It's just, well, finite automata as usual, and the transitions have weights. Here, the red number. So for instance, we can start here. In this state, we can execute A with cost 1, we can execute B with cost 2 and go back, or we can execute B with cost 1 and go here. And finally, we can leave it with cost 0, or we can leave it here also with weight 2. So a path, a sequence of transitions, is defined as usual. And now suppose that we compute in the real numbers, non-negative real numbers, together with minimum and plus. If we have a path, so a sequence of transitions like this one, for instance here, then first we need some cost for entering the system. Then we have the costs or weights of all the transitions. And then we need some cost. We have some cost for leaving the system, and we add them all up. So this gives the total weight, the total cost for executing the word along this path. And we might define the behavior of the automaton in the following way: as a function from A star into the non-negative reals for any word. We look at all the paths P realizing this word. They're at the weight of the path given in this way, and then we take the minimum. So we have the optimistic point of view that the automaton chooses the path with a minimal weight. Yeah, and okay, so a longer path we take plus, of all paths we take minimum. We might also do it differently. We might do it with, instead of minimum and plus, we might do it with maximum and plus. Here the roles of infinity and minus infinity are, if here, for instance, you don't see infinity here, and the reason is a transition which has an infinite amount of cost is simply impossible. I cannot execute it. Yeah, so I could put in lots of arrows here for the transitions which are impossible actually and give them all weight infinity. Then if we add it up, it will immediately be infinity. And if we take the minimum, we can disregard infinity. And this means we disregard impossible paths. Okay. And for maximum, we can compute with maximum, then we take the maximal cost. Yeah, this would give the maximal cost for executing a word, and if that is okay, well, then we are fine. The weights might also be in the interval 0, 1 and mean probabilities that the transition is successful, so the reliability of the system, and then along a path we would multiply. Yeah, we would multiply the weights, the probabilities that all transitions are successful, and then we get the total probability that the whole path is successful, and then we would take the maximum. We take the path which has the maximal reliability. We might also take real numbers with max min. This is kind of a channel model. If we think of a system of channels, it's supposed each channel is supposed it's built up with atomic pieces, atomic channels, and if we want to talk about the capacity, how much can flow through, the simplest model is along a path of pieces of channels. We take the minimum over the capacities because this is the most narrow piece, and this amount will certainly flow through without any difficulties. And then over all possibilities, over all possible paths, we take the maximum. Okay, we might also take 0, 1 with supremum and infimum. And so the Boolean semi-ring, and here the actual transitions and the initial and final weights get value 1. And if we are at the path, we take the second operation, the infimum. So we get a 1 only if all transitions have value 1 and initial and final states have value 1. And this means the path is possible. And then we take the and successful because initial and final states have value 1. And then we take the disjunction. So a word has a successful path. A word is accepted if and only if there is a path which has value 1. And in this way, we can incorporate all classical non-deterministic automata into this weighted setting. Yeah, so this generalizes all of automata theory, well, for finite automata into a weighted setting. We might do the same thing as here, giving weights 0 and 1 to all transitions and initial and final states, but now we compute in the natural numbers with plus and times. If we multiply zeros and ones, we only get zeros and ones, and that's actually the same operation as the infimum of 0 and 1. So along a path, we get a 1 if and only if the path is successful. But now over all paths, we take plus, so we sum ones, and this means we have a 1 if and only if the path is successful. So in total, we get the number of successful paths for W. Yeah, so this the previous model tells us, well, word, is it accepted? Is there a successful path? And the automaton says yes or no, there is one. And this model tells us, well, yes, it's accepted, and maybe there are 5 successful paths, exactly 5. Yeah, so that's the advantage. We get a more precise answer. How often is it accepted? How many successful paths are there? Okay, so the common feature, what's the common feature among all these different structures? The common feature is that we have a semi-ring. The semi-ring is actually defined very easily, just like the natural numbers. We have 2 operations, plus and times. With plus, it's a commutative monoid. With times, it's a monoid. Doesn't have to be commutative. If it is commutative, then we say we have a commutative semi-ring. Multiplication distributes over addition, and the 0, the neutral element with respect to plus, acts like a multiplicative 0. X times 0 equals 0, and 0 times x is also 0. Then the weight of a path is defined by, well, taking the cost for entering the path, then the weights of the transitions, and then the cost for leaving the path, and multiplying all of them. And the behavior is given by the following function. For any word, we look at all the paths, realizing the word at the weight, its total weight, given in this way, and then we sum it up. Yeah, and formally this may be written in this way, and it's some authors call it a formal power series over K and A star. And then the problem is which functions arise as behavior, as quantitative behavior of these weighted automata. Okay, so as an example, consider this automaton here. We have only one state. It's initial and final with weight 0. We can execute A with weight 1. We can execute B with weight 0. And the longer path, well, it has the path only touches, there is only one state. So we stay in this state. Along this path, we add up the weights. So, and then over all paths, we take minimum, but this doesn't matter because we have only one state and only one path. So what is happening here, if we have a word, we start with weight 0, then we add a 1 if we have an A, we add a 0 if we have a B, and so on. And then finally, we add 0 again for leaving it. So in total, we get the number of A's. Yeah, to any word, this automaton tells us for any word the number of A's. Now, how do we incorporate the classical automata or theory into this concept to make this to repeat this a little bit? We take the Boolean semi-ring, and if we have a language, it is replaced by the characteristic function 1L, which assigns to W 1 or 0, 1 if W is in L and W 0 otherwise, and then L is recognizable if and only if this characteristic function is the behavior of some weighted automaton. Yeah. And in this way, if one wants to extend the classical automata theoretic result into weighted automata, one first thinks, how can it's the classical result is about languages. How I formulate this as a result over characteristic functions in the Boolean semi-ring. And then, well, yeah, then I replace the Boolean semi-ring by an arbitrary semi-ring, or maybe commutative semi-ring. And then we see whether the proofs still work. Okay, applications of weighted automata, they are used for, have been used for data compression for digital images, and they are still being used for speech recognition. And they also solved some problems in theoretical computer science and formal language theory, which this is on equivalence of unambiguous context-free languages, for instance, and which could not be solved without weighted automata so far. So very soon some books came out by Eilenberg, Salomar Solte, Lacuich, Salomar, Berstl-Reutenauer, and then the Handbook of Weighted Automata, which Guillermo kindly also already mentioned. Okay, so far we have seen this correspondence between automata and logic, the result of Büchi and Elgot, and the extension to weighted automata. So now the question is, can we extend the logic to some weighted logic such that we get an equivalence result here, which extends the equivalence result of Büchi and Elgot? So we want to have this weighted or quantitative logic, and given a sentence phi, its behavior should be the same as the behavior of a weighted automaton. So it should be a function from A star into K. For instance, it might map a word to the number of A's. Yeah, so that's our goal, and we want to define syntax and semantics now for formulas with weights. Okay, so we do this in the following way. Given an alphabet and a semi-ring K, the syntax of weighted formulas is given by the following grammar. First, we take any constant of the semi-ring. Then we have RA of X, meaning that at position, yeah, okay, RA of X, X smaller than Y, and X in X. These are the atomic formulas, just as in classical logic. We have negation, disjunction, conjunction, existential universal quantification, both for elements and for subsets. Yeah, and we will need conjunction here and universal quantification, and I will give the reason in a second. Now let's come to the semantics, And we do this by induction over the structure of phi. So we want to give it for a word. And as usual, well, if we have a formula with 3 variables, we have to know what do we put in for the variables. So we need an assignment of the variables to positions or to sets of positions for the set quantifiers, set variables in W. And then we define the semantics of phi for W and this assignment, well, by induction over these formulas. So for a constant, it's very easy. As semantics, we take the constant itself. For atomic formulas, it's also very easy. Let's look at this one first. X smaller than Y. What's the semantics for W or sigma? For the atomic formulas, the semantics is always 1 or 0. So here we put it 1 if it is true. So if X is really smaller than Y, and with this I mean, well, X and Y are variables. I mean, of course, the positions which are assigned to X and Y by sigma. So if sigma of X is actually smaller than or equal to sigma of Y, then it's 1, otherwise 0. An array of X, similarly, if at position X we have an A, well, at the position assigned to X, and if I assign to X position I, then the ith letter AI should be equal to A. Then it's true, and then it's 1, and otherwise 0. X in X, similarly, if the position assigned to X is in the set of positions assigned to capital X. Negations, how do we do negations? By induction, well, if phi has value 0, then we put 1. And if phi has, well, does not have 0, like, for instance, in the natural numbers, it could be 5, then the value is 0. So note that double negation does not give the same result, because if we start with 5 and negate it, we get 0. And then if we negate it again, we get 1. Yeah, but that was noted already in the 1930s, and when people developed many-valued logic, they already thought about this and proposed also this solution. Another possibility is to restrict this only to atomic formulas, and then we would get only 1 and 0. Okay, for disjunction, we take plus, we take the values and then add them. And for conjunction, we take multiplication. And now this is the reason why we will need multiplication, because in classical logic, we can express conjunction by disjunction and negation, yeah, double negation, the De Morgan laws. But here we can't do it. If you think about the natural numbers with plus and times, how should we define the multiplication or represent the multiplication? By using plus and then only this negation. Yeah, this is not possible. So we really need an operation for times, and therefore we will need conjunction. Okay, for existential and universal quantification, existential quantification basically is a big disjunction. It means there is a position, so the position is 1 or 2 or maybe length of W, yeah? And for all these possibilities, we already have these values and we sum them up. Like in disjunction, we took the sum. In conjunction, we take the product. And for the universal product, we have all possibilities from 1, 2, and so on until length of W. So we take the values and multiply them. And for the sets, correspondingly, we look at all the subsets I of the universe. So we invented this for the words and the automata this was with Paul Gastin in 2005. Okay, now if we have the classical Boolean algebra 0, 1, we get back classical logic. And if we have an arbitrary Boolean algebra, we get a very natural multivalued logic, yeah, where the values are taken in some arbitrary Boolean algebra. Okay, now, but we might take the set of the semi-ring of natural numbers, and now I want to show you, give you a reason. If phi is an MSO formula, then the semantics is the number of proofs that W satisfies phi. Yeah, so the semantics is the number of reasons why phi is true. This is what I wanted to have as a goal. Yeah, the number of reasons. How often is phi true? And here in a, well, even more exact setting, how many proofs do I have? Now, proofs is not given in a proof theoretic setting, yeah. So I don't give the axioms and the rules and so on. So this has to be interpreted well, a little bit intuitively. But let me give you. We will work through the induction of phi. So let me give you the reasoning for this. Well, for the constants, we have to leave out the constants, yeah. So the semantics is K. Now, for the atomic formulas, and we apply negations only to the atomic formulas because, you know, we can pull them through in a formula until they are in front of the atomic formulas. An atomic formula is either true or not. Yeah, we check whether x is smaller than y, respectively the positions assigned to x and y. And so there is precisely, it's true or not, and there's one reason for it. So we get 1 or 0. But the interesting case is phi or psi and phi and psi. And how many proofs do we have for phi or psi? Well, how do you prove phi or psi? You have to give a proof of phi, or you have to give a proof of psi. And in fact, you can choose any proof, whatever you like. Yeah, we have this number of proofs for phi, the semantics of phi, and this number of proofs of psi, semantics of psi. So in total, we have the sum. Yeah, and we can choose any proof, and this is the total number of proofs for phi or psi. Now here you might say, of course, okay, what happens if phi equals phi? Yeah, then this should be phi, and then I should get only phi. Here I get the sum. Well, if phi equals psi, well, that's true, but we look at it in this way. I want a computer to print out the proofs. Yeah, the computer should print out the proofs one after the other. So if here I have phi or phi, and I did not program the computer to check this first, but just to print out the proofs of phi and the proofs of psi, then it will print out these proofs and it will print out these proofs, and in total we get the sum. Yeah. So this is why I think it's okay. What about phi and psi? How many proofs do I have for phi and psi? Well, here I have to prove phi and I have to prove psi. And I can take any proof for phi and pair it together with any proof of psi. So how many proofs do I have? Here I have this number of proofs of phi, this number of proofs of psi, the semantics. I can pair them together in any way. So the total number of pairs is the product of these two numbers, and that gives me the total number of these proofs. Yeah. And same thing for existential and universal quantification. The total number of proofs of this, well, I can give a proof for any position. Yeah, this can be any position here, and the number of proofs is given by this, and then the total number of proofs is the sum of all these numbers. And for conjunction, well, I have to show that phi holds at every position which I put in for x. Yeah, it has to hold at position 1, at position 2, and so on, and at position length of w. But I can choose any proofs of them, of these for any position, and the total number of proofs then is the product of these numbers. And similarly for set quantifiers. Okay, so I think this gives the semantics, well, gives a number of arguments maybe that why phi is true. Now let's look at phi equals, there is an x such that R of x. This means there is a position in the word such that at this position we have an A. So if we look at the semantics, here we take the sum, yeah? We take the sum over all I, and this, what was this at value I? This was here, we have a 1 if really we have an A at position I. Otherwise, we get 0. So we add in this existential quantifiers, we add ones. So this means here we add ones when we have an A. So in total, we get the number of A's in W. Yeah, this is the semantics of this formula. Now, if the semi-ring, so I think this is very nice. Yeah. So here we have the number of arguments. Here we get the actual number of A's. So the question is there a position which is labeled with A? That's in classical logic, the question, and the answer is yes or no. The word contains an A or it doesn't. Here, if I ask myself, is there an A in the word? The answer is, well, yes, there are 5 A's, for instance. Yeah, so I prefer this answer. It tells me how many A's are there in the word. Yeah, and because I want that point, is there an A? Well, I could point to the first A or the second occurrence of A or the third occurrence of A and so on. And moreover, this is meant in the semiring. So if we have the semiring of natural numbers, we get the actual number. If we have the Boolean semiring, we get yes or no, so it contains the old answer. But if we have another semiring like the field with 2 elements, then we get the number, well, yes, there's an odd number of A's or an even number of A's. Yeah. So depending by varying the semiring, we also have some flexibility in interpreting this number. Okay, so now our goal was to show that the recognizable functions are definable to extend Büchi's theorem, and the question is. Do we get this extension of the Büchi-Elgort theorem? And unfortunately, the answer is no. If we have a weighted automaton, that function is definable. Yeah, we can go from the left to the right, but not the other way. There are sentences where the semantics can be described by a weighted automaton, but as soon as I put in universal quantification in front of them, I cannot do it anymore. And this holds even for the semiring of natural numbers. So we want this to, well, semiring of natural numbers is, of course, well, one of the most important semirings. Yeah. So we have a problem here. And the reason is the universal quantifier. And there are several solutions for this. And a very nice one was given by Bollich and Gastin in the following way. Well, we have to restrict the use of universal quantifiers. Yeah, in the following way, we define the Boolean formulas in the following way. We take the atomic formulas, and then we take negation and conjunction and universal quantification. And note that here we have the full power of MSO because we can define disjunction by conjunction and negation. Yeah, if we just take the logic. And the values here, all of the values are 0 or 1. Yeah, because the atomic formulas get value 0 or 1. If we negate it, it's 1 or 0. If we here, for the conjunction and the universal quantifications, we take the product. So the product of zeros and ones is just zeros and ones. So as values, we get only zeros and ones. And it turns out the quantitative semantics of a formula, such a formula is 1 or 0. And it's 1 precisely if the word is accepted by beta. If it's true for beta. Yeah, if it's true for beta. So these Boolean formulas get values 0 and 1. And our syntactically restricted MSO, where we restricted the universal quantifier, is the following. Well, basically, we throw away we don't allow the universal set quantification, or let's say we allow it only if phi is Boolean of this form. And we allow the universal set element quantification and also negation only if phi is either a constant or such a Boolean formula or constructed from these using the disjunctive conjunctive closure. Okay, so then existential EMSO is given in the following form. We take a phi, which has only existential and universal quantification for element variables, and then we put some set variables with existential quantifiers in front of them. That's existential EMSO. And then we have the following result, which is joint result with Paul Gastin. Let A be an alphabet and K a commutative semiring. And let S be a function from A star to K. The following are equivalent. S is the behavior of some weighted automaton A. This is what I wanted to characterize, what I wanted to describe. And the description is S is the semantics of phi for some syntactically restricted EMSO sentence phi. Yeah, sentence, well, an existential EMSO and satisfying these restrictions. Okay, and the third one is S equals phi for some syntactically restricted MSO sentence. And moreover, if the semiring is locally finite, then we can take any MSO sentence phi in our weighted logic. Locally finite means any finitely generated sub-semiring is finite. For instance, if we take a Boolean algebra, or one could even take a distributive lattice with 0 and 1, then any finitely generated sublattice is finite, yeah, due to distributivity. So this contains any Boolean algebra. So here that we can, you notice if K is the Boolean semiring, yeah, the equivalence between 1 and 4 gives us the classical Büchi result. But this is more general because we could take any finite semiring, even any finite semiring, and then we have the equivalence between 1 and 4. And yeah, and also we could take any Boolean algebra because the Boolean algebra is locally finite, and we would also have this equivalence between 1 and 4. Yeah, the classical, and in this way we have extended the Büchi-Elgort theorem, and in fact this holds for any semiring, respectively for any locally finite semiring. The proof, 1 implies 2. Well, this works by analyzing the structure of the automaton and then and describing it by a sentence phi. 2 implies 3 and 3 implies 4. That's trivial because we allow more and more sentences. So we have to show, the work is to show 3 implies 1 and 4 implies 1 under the assumption that K is locally finite. And how do we do this? By induction over the structure of the formula. So for the atomic formulas, we can give the weighted automaton explicitly and right away. Then let's go through the induction. These atomic formulas, they are okay. For negation, that will also be okay. We can assume we apply, yeah, that will be okay. For disjunction, we use a classical result from weighted automata theory, from formal power series, for conjunction also, and for existential quantification also. For universal quantification, we have a problem. Yeah, and in particular for this one, but we excluded this one. So we only, because of big problems here, so we only allow this one in this setting. So here, under this assumption, but here, this is problem. This did not occur in the classical setting, Büchi and Elgort, because one can express the universal quantification simply by existential quantification and using negation twice. Yeah, we don't need it, but here we need it. And so this needs a new proof, yeah, an automata theoretic proof, how we can construct the automaton for this. If we have the automaton for phi, how do we get it for universal quantification? And that was the most difficult proof, yeah. And in all these settings for weighted automata, if we look at other structures than words, then this is always the most difficult proof. And for the universal set quantifier, we get it if the semiring is locally finite. Yeah, then it's also possible. Okay, as a consequence, we get, if we have two formulas and they are syntactically restricted, then, and we want to decide whether they have the same semantics. Yeah, do they have the same quantitative semantics? This is what we want to decide. And it's possible if the semiring is the field of rational numbers or Boolean algebra or some finite semiring, then it's possible. Because what do is we construct the automaton, our proof, which we have here from the formulas to the automaton, is constructive. Yeah, we get the automaton. And so we construct it here, and then we check the equality of the semantics of the two automata. And if it's a Boolean algebra or finite semiring, it's possible relatively easy. And if it's a field, it's also possible and even quick. Okay, the problem is from going from the formula from the sentence to the automaton. Now, if we have the min plus semiring, then the equality is undecidable. This is a result of Grob because it's undecidable for the weighted automata. Yeah, if this was decidable, then we would also have a decision procedure for the weighted automata, but by Daniel Korb, this does not exist. Okay, so people have also looked at these weighted automata with another semantics, namely the following. We looked at for a path, we looked at the sequence of transitions, and then we summed up their weights. Yeah. But one might also be interested if you think about a technical system, like maybe an energy plant, yeah, creating energy. We might also, of course, if we take the sum, this will increase. Yeah, if we look at the long range with n trending to infinity, this will simply increase and it will go to infinity. So, but what's more interesting is then to take the average. We want to know how much do we use on the average, because we also have some income, yeah. And then the question is the average approximately okay? So we would take the average here for the weights along a path, and then the maximum. Yeah, what's the maximal average which we use? So, and actually we can do it in a more general way. We can replace average by a valuation function, which gives to the sequence of transitions, we get some weight in some way. Another valuation which is looked at a lot is for instance, discounting. We count the first transition full. The second one, the value gets multiplied with some delta. Delta is smaller than 1, and then with delta squared, and so on. Yeah, and then we sum them up. Okay, and this gives me the weight, the weight for the automaton, and the question is, can we describe it? Do we have an equivalent weighted logic? And in fact, we have. Given an alphabet, a commutative for simplicity. There's also a result if k is not commutative, but let's make it commutative. And the function, the following are equivalent. S is the behavior of a weighted automaton. S is the semantics of such a sentence, which is syntactically restricted and EMSO. And or S is the semantics of a syntactically restricted sentence. Okay, what about the logic? Yeah, we have to change the syntax and the semantics. And it turns out we can take the same syntax as before for semirings, and we can even take almost the same semantics here. In spite of dealing with this complicated average evaluation or even discounting or so, we can take the same semantics, almost the same semantics. The only thing which we have to change is the semantics of the universal quantifier. Here we take we look at the values of phi for all possible positions. This is this, yeah, for W and position to X, we assign position I from 1 to length of W, all these values. And then we take the valuation of this sequence of values. And the valuation might be the average, or it might be discounting, or in the classical case, it's just the product. Yeah, it was just the product in the same ring. We only take this, and then the same result works again with very, very similar proofs. And we have a corresponding result also for infinite words. Okay. And now I want to come to something more recent, but let me start with the following result of Fagin from 1974, which says that the complexity class NP is equivalent to second order logic to E with existential quantifiers in front to existential second order logic for finite sigma structures. Yeah, sigma is a signature. NP is the class of all languages where there is a non-deterministic Turing machine which accepts L, which accepts L in polynomial time. So there is a polynomial such that each word is accepted in length bounded by the polynomial applied to the length to this word. And ESO is existential second order logic. Yeah. And he proved this equivalence result, and this is interesting because here we need a non-deterministic Turing machine, and we need some automata theory. Yeah, do we accept the language in polynomial time? And so this is getting really getting into dealing with automata and their behavior. yeah, automata theoretic behavior. But here we got rid of all the difficult technical questions, and we have a purely logical characterization. Yeah, this is pure logic, existential second order logic. And so this founded the area, the field of descriptive complexity theory. Yeah, because it describes complexity by the logical components, logical concepts. Okay, so we extended automata to weighted automata, and the question is, can we extend Turing machines to weighted automata? Yes, we can. And then the question is, can we extend this? We extended logic to weighted logic. Can we extend existential or second order logic to weighted logic? Yes, we can, basically in the same way. Yeah, and we can do it not only for words, but for relational structures. Yeah, that's clear. That's how it has been done already for decades in many valued logic. But the question now is, do we get this equivalence here in some weighted version? Yeah, and I'm very happy to Guillermo that he said we should look at this question and yeah, and work on this. So the result is jointly with Guillermo and Carlos Noguera and Eric Paul from Leipzig and myself, and published this year at MFCS. Let S be a semi-ring, sigma a vocabulary, then a weighted version of this of NP over the semi-ring S, yeah, with weights in S, is equivalent to a weighted existential second order logic, yeah, with weights in S. And equivalence here means that a weighted Turing machine and the weighted sentence give the same values for all ordered structures. Yeah. So this means two things. For any weighted Turing machine, well, which for every run, for every word, there is a successful run whose length is bounded in polynomial time. Yeah. So for every such Turing machine, there is a sentence in W in weighted existential second order logic, so that we get the same values for any finite ordered structure. And the other implication for any sentence of this form, we can model it by some weighted Turing machine, so that again we get the same values. Yeah. Here we can define the value for a finite structure of this sentence right away, just as by induction, just as usual. And here we have, of course, we cannot put in the relational structure into the Turing machine, because the Turing machine has a fixed alphabet. So we have to code, this is the encoding of this structure, well, as a sequence of zeros and ones. Yeah, we can code everything as a sequence of zeros and ones. We have to code the structure in some form so that the Turing machine can deal with it. And that's what we do. This holds for all finite ordered structures, and it even holds for all finite structures if the semi-ring is idempotent and commutative. So this includes the Boolean semi-ring. Yeah. This holds, yeah, so the classical Fagin theorem, by if we put in the Boolean semi-ring, we get it back, yeah. But it holds for more semi-rings like the max plus and min plus semi-ring, which we had, yeah. Maximum and minimum are idempotent and plus is commutative. So the important max plus and min plus semi-rings also fall into this category. And in the proofs, well, as I already indicated, for M, we have to define, construct phi, and for phi, we have to construct M. And then we need an exact correspondence between the computation sequences, which get accepted by M, and the assignments such that phi is true. And moreover, the weights, so this has to be a bijection. Yeah, we have to get a bijective correspondence here. And moreover, then the weights have to be the same for corresponding computation sequences and assignments. Yeah, so we have to look at the classical proof. Just says, well, yeah, here there is an accepting path, and here there is an assignment which makes it true, but maybe there are many. And I don't care how many there are. Yeah, just it has to be there. There is one. If there is one here, if one here, there is one here. But here we have to have the same number and the weights have to correspond. Yeah, except if the simmering is idempotent, then the numbers can be different. Then it doesn't matter. Okay, so and in this way we get this this equivalence results. Okay, and then we also looked at some other results which came off some other complexity classes which came after Fagin's result. Okay, so weighted automata and weighted logics. Well, they were introduced for words by Paul Gaston and myself, and then they were extended to this correspondence to trees by Heiko Vogler and myself. So in all of these settings here on the left, there is an equivalence result in the classical case for the Boolean simmering, and then on the right, it's extended to the weighted setting. One can look at infinite words. This is what I did with, I did this with George Rahonis, and he looked at infinite trees. One can look at traces, which are, well, free partially commutative monoids, and they have been used for distributed systems. One can look at texts and nested words, was done by Christian Matthiesen and Stefan Dück, and one can look at pictures, which are, well, rectangular words, two-dimensional words by Ina Meurer, Paravane Barbari in PhD thesis. One can look at timed words for real-timed automata. Karen Quas did this. Several people have looked at probabilistic CTL, and Borlich and Gaston, they showed that probabilistic CTL can be embedded into weighted logic. So if you like probabilistic CTL, then, well, you can also phrase this in weighted logic. Weighted expressions is another formalism. It was done by Zoltan Fülöp and Heiko Vogler. One can look at multi-weights. So one might not only have a cost for an action in a system, you might also gain something. Yeah, so you have a win and a cost. So, and the longer path, you would ask yourself, okay, what's my total win and what's my total cost? And then you take the quotient. Yeah, so one needs, and then you have the real win, yeah, for the costs. And so we have multi-weights. These were considered by other people, by several, independently by several research groups. And what we did was we derived this Büchi-Elgort theorem. It works not only for finite automata, but also for push-down automata. This was, well, joined with Vitaly Perevoshikov. And if it is true for so many structures here, the question is there a general result? And in fact, there is. One can do it for graphs, yeah, for graphs and weighted graphs. And then, okay, push down automata, but here things get undecidable very quickly. So because of this, Mandrioli, Pradella from Milano investigated operator precedent languages, and one can also do it in a weighted setting. Well, and most recent result in descriptional complexity, one can also do it in a weighted setting, yeah, with Guillermo, Carlos Noguera, Eric Paul, and myself. And well, so maybe the next one will be by you. Well, thank you very much for your attention.